Welcome to today's webinar, running fast interactive queries on petabyte data sets using Presto on Amazon EMR. Our presenter today is Keith Stewart. Keith is a specialist solutions architect at Amazon Web Services in Boston, and he specializes in the Amazon EMR Hadoop as a service. He helps customers understand and architect solutions using Amazon EMR, Apache Hadoop, Apache Spark, and other AWS services to achieve business aims. Today with us, we also have Jorge Lopez, Kevin Fallis, and Chris Marshall. They will serve as our webinar moderators and will be engaging with you and answering your questions throughout the presentation while Keith presents. Keith, welcome. The floor is now yours.
Hello, everyone. Welcome to the webinar. Thanks for attending. Today we're going to talk about how you can deal with petabyte-scale data using something other than a data warehouse. Obviously, everybody's accumulating large amounts of data, and the traditional solution of a data warehouse does have some challenges. So we're going to talk about how you can use an alternative approach using Presto on EMR. So here's what we'll cover today. We're going to start out by looking at data warehouses and reviewing some of the challenges associated with using data warehouse technology. Then we'll take a look at an alternative, a non-data warehouse approach. We'll walk through the high-level steps involved in this alternative approach. We'll look at some of the components of the solution, in particular Amazon S3, Amazon EMR, Apache Presto, and then how you combine all these things together on EMR to accomplish the solution. And then finally, we're going to look at a demo. We'll put all these things together and show you a real-world example using a set of data that's 29 years of air flight data, including delays and cancellations and that kind of thing. That data is on S3, and we're going to use Presto on EMR to query it. All right, so let's jump in and review data warehouses. So data warehouses follows a paradigm referred to as schema on write. And what that essentially means is that raw data files have to be extracted. So subsets of the fields, attributes are extracted. And then there's a significant amount of cleaning, coding, analyzing, aggregating the data, and normalizing the data, followed by a loading process to load it into a data warehouse with a defined scheme. And that is, the schema is thought of as a universal schema. It has to accommodate all the different types of data you anticipate working with and structure it in such a way that it's useful. And then at that point, once the data is in the data warehouse, the business analysts and the data scientists, they can then start working with the data, doing data discovery to learn about what kind of data they have and to run particular queries against it. There are at least a couple of challenges with this older paradigm now. There are at least a couple of challenges associated with this. The biggest one is that data warehouse technology tends to be proprietary, sometimes even proprietary hardware. That makes it very expensive for most organizations. The other thing is that because of all this upstream processing of the data before it can be looked at, there's a significant time to answer delay. And so, it impacts agility and the ability of people to get rapid access to the data. Right, so we have the schema on write paradigm. An alternative is a schema on read. And in this case, rather than structuring the data up front and then writing it to this universal schema, we leave the data in its raw original form. And that data goes in and is stored in a Hadoop cluster in a distributed fashion and stored unmodified. And then on an as needed basis, on a query by query basis, the data is queried and structured at the same time on the fly. And so there's some minor processing, but it's done on a per query basis. And so the benefits, well, number one, because it uses Hadoop cluster technology, it's significantly cheaper than a data warehouse. Because there's much less upstream work involved, and because the data, once it's in the cluster, is immediately available for querying, there's a much shorter time to answer. So there's a big difference then in terms of agility and economics and in terms of working with petabyte scale data. The other difference is that in the data warehouse, because you have to come up with one schema that represents and structures all the data in a consistent way, there's a certain amount of rigidity associated with what kind of queries you can execute. In the schema on read, where the data is sitting in the cluster in its raw original form, there's much more flexibility in terms of the kinds of queries that the business analysts and data scientists can execute. All right, so how do we work with petabyte scale data in a schema on read fashion? Well, there's 6 relatively simple steps. Number 1, you store your data on S3. 2, you configure and launch an EMR cluster, making sure Presto is present. You log into the cluster. You expose that data that's on S3 as one or more Hive tables. That makes it available for querying. And then 5, you issue your SQL queries using Presto against those tables as defined in Hive. And then 6, you get your results. We'll see this in action towards the end. So let's talk about the components. So S3 is a key component in this schema on read paradigm. S3 is often called a data lake. It gives you a place to store all your data from all your different sources, all in one place, so you have the ability to work with it and work across the different data sets. S3 is a massively parallel object store. It's an object store in the sense that it can store a single byte text file, or it could store a 5 terabyte video file. So it's very flexible that way. It's scalable and elastic. What that means is that as much data as you have, you can send to S3, and S3 will accommodate it. It's elastic. You don't need to pre-provision any capacity. The capacity is there no matter your amount of data. Another attribute is 11 nines of durability, so your data is protected and safe and sound on S3. There's effectively infinite bandwidth. As many threads and as many multi-part upload processes as you can run, S3 will accommodate it. And it's very low cost, about 3 cents per gigabyte month and about $30 per terabyte month. Very economical. And very importantly, S3 is a foundational layer for virtually all of the AWS services. Once your data is in S3, it's essentially future-proofed. You're able to move it in a variety of ways to different services. Looking at that specifically, this shows a few examples of the kinds of other systems that can move data in and out of S3, including EMR, which you'll see shortly. Kinesis and Kinesis Firehose, which allows potentially millions of devices and endpoints to send data from the internet into S3. Data Pipeline is an orchestration service for doing various workloads with the different AWS services. Redshift, our data warehouse. DynamoDB, a NoSQL solution. RDS, the relational data service for various relational databases. Moving data in large amounts overnight can be accomplished with the import-export service. Last year we announced the Snowball appliances. These are 50 terabyte to 80 terabyte appliances that can be FedExed to your location. You put your data on those and then they get FedExed back to AWS, where your data then shows up in S3. Additionally, Spark and Spark Streaming can work with S3, and massively parallel systems like Storm can also work. So if your data is in S3, How do you expose that in a way that massively parallel compute systems can perform queries on it? Well, here this illustrates that. Here's a bucket within S3 called flight delays KLS, and we'll see this during the demo. There's a hierarchy here showing a subpath called CSV. We've got some comma separated value data, and then this additional hierarchy, which is actually a partition. We've got year equals 1987 in this case. Partitioning is a best practice when you're storing your data in S3. Partitioning essentially adds entropy or uniqueness to the path of any objects in S3, and what that does is maximize the parallel I/O and minimize the chance of hotspots. So if you spread your data files out over unique paths, you maximize the I/O. And in this particular location, year equals 1987, we've got a CSV file for 1987 that's been bzip2'd. If you wanted to expose that set of, and we have multiple years, 29 years, this is just showing one example, but if we wanted to expose all this CSV data in a form that could be queried by massively parallel systems, we would take advantage of Hive. Hive is, as many of you probably know, is a key component within the Hadoop ecosystem, and Hive is essentially a directory or database of databases, and it makes all the data defined and accessible to other systems. So we would go into EMR, which we'll talk about shortly, run Hive, and then we would tell Hive to create an external table corresponding to that location. And so here's the location, flight delays KLS with the CSV, and what we do is we specify how the fields in this comma separated flat file should be interpreted. And so you can see things like year, int, quarter, int, etc., strings, and so on. And then it's partitioned by year. So that information is available. That allows for faster querying because of the partitioning. And we're telling it that the format for that flat file consists of fields terminated by commas, escapes, and lines terminated by new lines. So once we've created the external table, then Hive knows about that data. Now, it's very important to keep in mind that we're not copying data from S3 to some other location. We're not transforming the data. We're leaving the data as it is in its high fidelity original form on S3. All we're doing is declaring the existence of that data on S3 and superimposing an interpretation of that data so that then it can be queried. So in this case, if we go in now and ask Hive to describe this error delays table, this external table, it'll in fact show us the structure that should be used to interpret it. Right, the next component is EMR. EMR is a scalable Hadoop clusters as a service. It's scalable in the sense that you have the choice of however many nodes you want to use, the types of EC2 instances you want to be part of it, and you can dynamically resize the cluster up or down to suit the workload that you're working with. We have 15 applications, Hadoop applications, ready to install on EMR with the simple check of a checkbox, and you'll see an example of that. You can also, if you're familiar with the AWS command line, you can spin up an EMR cluster and specify the applications as parameters in that command line call. It's very easy to use and it's fully managed. The simplest version is like a single web page with a small number of fields to select from, and then a button to submit that. And at that point, the configuration is done and the cluster starts spinning up. And that takes less than a minute to do that configuration. The cluster comes up in about 5 to 10 minutes typically. It's fully managed, so AWS looks after the service, the automation, the capacity, so that you can focus on your workload and getting the analysis or the processing done. You have three different ways to pay for EMR. You can use the standard on-demand pricing, hourly pricing for EC2 instances. With reserved, you can commit to using a certain number of EC2s for 1 to 3 years and get a discount because of that commitment. And then finally is spot pricing. Spot is there's a spot market of EC2 instances that have not yet been allocated to customers, and rather than having those sit on the sidelines idle, we make those available to customers to bid on, and so they can specify their maximum bid price. The actual price they pay for those spot instances is the spot market, and as long as the spot market price remains below their bid price, they'll continue to hang on to their spot instances. The trade-off for using spot instances is if the spot market does rise above your bid price, there's some risk that those spot instances could be taken away from you. Now, EMR is robust enough to handle, redistribute jobs and deal with things so that the work continues. But with spot pricing, the real advantage is oftentimes you can see an 80 to 90% discount on the hourly rate as compared to on demand. So spot pricing is a huge bargain when doing massively parallel computation. There are three different persistence technologies for your data with EMR. You can of course use the standard HDFS that Hadoop originally had. Most importantly is S3, and we'll take a look at how that works. S3 gives tremendous benefits and gives you the ability to work with petabyte-scale data at great with great economics. And then finally is EBS, elastic block storage, where you can attach additional network-mounted disk space to your EC2 nodes in the cluster to give you additional disk space. Now, keep in mind that in both HDFS and EBS file systems, but not S3, the storage is ephemeral. What that means is if the EMR cluster, if you terminate your EMR cluster, whatever data is stored on HDFS, which are the local node storage, or on the EBS volumes that are attached to the nodes, that data will go away. So keep that in mind. S3 is different, and we'll come to that shortly. Very importantly, with EMR, you have the capability to implement end-to-end security, providing encryption both at rest and in transit. One of the key innovations within EMR, which distinguishes it from other Hadoop distributions, is a component called EMRFS. This is the data abstraction layer that allows EMR to talk to S3, both in terms of reading and writing. Under the hood, it does a lot to enhance performance, and it handles error handling, and so it provides high performance and robust interaction with S3. It's transparent, so the only change you need to make is in the prefix in your data URIs. So instead of HDFS : / you would substitute it with S3 : / and then the path to your data on S3. S3 itself provides both server-side and client-side encryption, so you can leverage that for things like HIPAA and PCI workloads. EMRFS does some optimizations to provide for faster listing of objects. And then importantly, HDFS is still available. You can still use that. You're not obligated to use S3. You can, in fact, move data easily between S3 and HDFS, and so that's still an option. Okay, what are the benefits of S3 if you use that as your primary persistent data store for EMR? Well, we've already talked about some of the benefits itself that S3 itself has. The 11 nines of durability protects your data, and most importantly, the use of S3 as your primary persistent store decouples storage from compute. And this is very different than traditional Hadoop clusters that you might deploy on-prem or on your own fleet of EC2 instances. When you deploy your own cluster, you are leveraging um, a tight bundling of CPU, memory, and disk space. So if you need to expand either the storage capacity of your on-prem cluster or you need to accelerate jobs, you have to add additional nodes. But that means then you're also adding, in the case of if you're adding more storage because you need to store more data, then you're also adding more CPU and RAM, which you're also paying for. If you have less data, but you have to compute in a tighter SLA, then you're also adding disk storage, which you might not use, but you're paying for. So that tight bundling kind of restricts the flexibility for expansion of your cluster and significantly impacts the cost. Uh, Alternatively, with the storage of data in S3 and the compute on EMR, you are able to benefit from the flexibility of both storage and compute. So the storage, as we mentioned already, grows elastically. This capacity is always there. Whatever your starting amount of data, whatever the growth rate of your data, S3 is already there, nothing to pre-provision. You're going to be able to store your data. So you don't need to worry about storage, it's covered. On the compute side, you have the flexibility to right size the compute. What that means is you can look at your workload or workloads, you may have more than one, and be able to size the cluster and design the cluster to fit that storage need well. Going back briefly to the on-prem, you are usually provisioning, over provisioning in order to accommodate the largest workload and SLA that you need to meet. And what that often means is that 80% of the time your on-prem or EC2 cluster may be sitting idle or underutilized. Um, with the right sizing of compute, you can choose the number of nodes appropriate to the workload. You can choose different EC2 family types depending on the type of workload you're doing. For example, if you're doing in-memory computation with things like Spark, you can use memory optimized EC2s. If you're doing significant statistical calculations, machine learning, etc., you can go with CPU optimized. And similarly, we have IO optimized EC2 family types. You can choose different sizes of EC2 instances. You can pick ones with 4 cores, 8 cores, etc. And you can resize your cluster up and down and not have to worry about losing your data. The data is safe and sound on S3. And very importantly, if you're doing batch processing of your data, once the batch processing is complete and your results, the input data came from S3, the output records went back to S3, you can shut the cluster down until you need to run the workload again. So you have a lot of flexibility that way. And then very importantly, you have the flexibility to run multiple EMR clusters that work concurrently with the same data set in S3. So you could have different size clusters depending on the different size workloads that you have. If you need to run workloads in parallel rather than serializing the queuing of the work, you have that flexibility. You might have a data science team that's iterating on some algorithm. They don't need a large cluster, they need something small and a subset of the data to test with. And you may want to separate dev, test, and production clusters. And so this gives you the capability to do that. All your data is in S3, all of those clusters can work with the data in S3. All right, so let's get started on the demo. What I'm going to do is spin up an EMR cluster. We're going to make sure Presto is installed. And while that cluster is spinning up, we're going to resume with the slides. So let me share my screen. So we're going to sign into AWS here. enlarge this. Hopefully people can see that. All right, so before I launch EMR, let's just take a quick look at the S3 bucket that we'll be using. Okay, we'll go down. Here's the flight delays, KLS. And as you see, we've got a CSV folders. These aren't really folders, they're paths, but you can think of them as folders. And we can look at the data file. So here's a CSV file that's been bzip2 compressed. I also have Parquet. We're actually going to work in the demo with Parquet. But at any rate, I just wanted to show you this is the data we're going to work with. Let's go back to EMR. All right, so let's create a cluster. And we'll call this webinar demo. And sorry, we're going to go to the advanced options. So we're going to pick the latest EMR. We have all the versions from the past available. We're going to make sure Presto is picked. It's labeled as a sandbox only because Presto is so new. Presto is in fact used in production, and we'll talk more about that shortly. So we've got that, we've got Hive, and we're covered here. Okay. All right, and then that's fine. Go with those defaults. We're going to go with our default network and subnet. Okay, so we've got one master node, two core nodes. We could pick different family types, as I mentioned, to work with different types of workloads, memory optimized, etc. But we'll go with the M3 mainstream. And let's throw in 10 nodes here of the task nodes. So the master orchestrates the cluster, manages the cluster. The core nodes are responsible for keeping track of HDFS data. So we just need two for that. And task nodes is what we'll use to accelerate the computation and to give us more parallelism. Okay. If we wanted to leverage spot, we could click here, and then we could put in our bid price, like 80 cents an hour if we wanted to, and it would pull those spot instances for us with the typical 80 to 90% discount. We'll just go ahead and use on demand here. All right, and these defaults are fine. Let's see, go with security. We're going to SSH into the cluster, so I'm going to pick an SSH key. Okay, and that's fine. Good to go. All right, so the cluster has been configured and it's spinning up. You can see how little time it took. There are lots of other additional features we could leverage, but for the demo, we can go with the defaults. If you wanted to, you could sit and watch the hardware spin up. So these are provisioning. Eventually, it'll give us a count of nodes as they're available. All right, we'll go back to the slides. Okay, so let's talk about Presto, the final key ingredient here. So Presto is open source software developed by Facebook. It's an interactive, massively parallel query engine. It's a SQL engine. It was originally designed to get around some of the limitations of Hive. Hive is also a query engine, as many of you know. Hive uses MapReduce. We'll see why that's significant. MapReduce does add significant I/O delay, and so Facebook wanted the ability to review their data quickly without having to wait for MapReduce. So hence Presto was developed for that. And as I said, it was open sourced back in 2013. What are the benefits? It's an in-memory distributed query engine, so it avoids the disk I/O for the querying. It's done in memory. Very importantly, it supports ANSI SQL. It provides a bunch of functions, user-defined functions, and roll-up and aggregation functions. It can work with a variety of data sources, which is important. If you're doing schema on read, you can pull your data from a variety of places to be able to do things like joins, etc. Yes, you can combine them in a single query. You can have joins, as I mentioned, and subqueries. And very importantly, the response times are very quick, within seconds to minutes for most queries. features. So it's very high performance. It's 10 times faster than Hive. Netflix, as a proof point, as I said, there are many production deployments of Presto. Netflix is just one of those. Netflix, they run 3,500 Presto queries a day on a data set that's 25 petabytes in scale, all of it sitting in S3, and they have on the order of 350 active users working with this data. It's extensible, a bunch of pluggable backends for different integration technologies, database stores, etc. Hive, as we mentioned. JDBC and ODBC connectors are available to support BI tools and dashboards. You can have different software clients talk to Presto, the Presto service, using HTTP and JSON. A variety of languages are supported. As I mentioned, ANSI SQL, you can do complex queries, which is in stark contrast to things like Hive and Pig and some other query engines. They are SQL-like, Hive is SQL-like, but they're very limited in terms of the kinds of queries you can do. Presto was explicitly designed to overcome those limitations. Very quickly, the high-level architecture of Presto, it's a distributed system, runs on a cluster of machines. The cluster is comprised of a coordinator that talks with multiple workers and dispatches work to the workers. Queries are submitted from a client, we're going to use one of them, the Presto CLI, which will run on the cluster itself. That talks to the coordinator and submits SQL queries. The coordinator parses, analyzes, optimizes, and plans the query, distributing it to the set of workers. In this diagram, it shows interaction with HDFS, but you'll actually see it working with S3. A little more architecture in terms of the sequence of events. There's a registration of all the nodes in the discovery server. The HTTP request from the client comes into the coordinator. It builds the query plan, distributes that to the various, well, it finds the nodes and then distributes the queries that way. Importantly, there's a pipelining architecture. So the rather than MapReduce, which tends to have a separation in time between the map task and the reduce task, the pipeline keeps things streaming through the nodes. And there's a variety of connectors to work with these different technologies. So why is Presto so fast? It does in-memory parallel queries. I mentioned the pipeline task execution. It optimizes for data local computation and does multi-threading. It caches hot queries and data, and you'll see an example of that in our demo. It does just-in-time compilation, SQL optimization, and other optimizations. One powerful one is predicate pushdown, where it can take the predicates from the query and push those down into the individual partitions. Let's see. So just to contrast Presto and its speed with MapReduce. So of course MapReduce, the original processing paradigm on Hadoop. As I said, there's a decoupling of the mappers and the reducers. The mappers transform the data, the reducers aggregate and roll up the data, and that may take place over several steps. The key thing is the disk I/O that happens between the mappers and the reducers, and also the non-pipelined interaction between the mappers and the reducers. The reducers have to wait for the mappers. Okay. So getting away from that, Presto cuts out the disk I/O and does everything in memory and exchanges data through the network. That cuts out the pipelining, also cuts out the wait time. There's no need for the fault tolerance. There is no fault tolerance, actually. Memory to memory data transfer, very quick, and everything has to fit within memory. So you have to consider that. Okay, so accessing petabyte-scale data sets in S3 with Presto, it's important to know that any table that's been defined within the Hive Metastore can be accessed and queried by Presto. So as soon as it's defined within Hive, it's ready for Presto, including data in S3 that's exposed via the create external table. There are different Metastore deployment modes. So the Metastore is how Hive manages the set of data objects that the cluster will work with and that the queries will execute on. The Metastore can be deployed in a variety of ways. The simple way for doing testing, unit testing, and that kind of thing is to deploy it all within the same process, okay, shown in light blue. An alternative is the local mode where you decouple the database persistence. So all the persistence is in a separate database outside of the processes here. And then finally is a remote mode where you fully decouple the client, the server, and the persistence of the data. Variety of data sources are shown here: Hive, Cassandra, MySQL, Postgres, and then pub/sub systems like Kafka and Redis. Okay, so when would you use Presto and when might you not want to use it? Presto is very good when you need fast interactive query and you need it with a high concurrency, large numbers of simultaneous users, and you need sub-minute responses. Another need is if you have a preference or a requirement for ANSI SQL, Presto will give you that capability. Where you might not want to use Presto is if you are primarily doing batch processing, particularly mission critical batch processing for large data sets. You have to keep in mind that Presto is a query engine. It's not for writing to persistent stores. It's for querying. So Hive would be the way to go. Hive is the way to go if you're actually processing the data and writing it out again, doing extract, transform, and load, enriching the data, etc. So Hive or Spark would be recommended in that case. If you're going to compute over the data that you retrieve from a query, for example, doing machine learning, graph algorithms, Spark is the one that would be recommended there. There are, as I said, there are user-defined functions and end functions that you can run with Presto, but if you want the maximum flexibility, Spark is the way to go. If your data is primarily star schema organized, then you would probably want to use a data warehouse, which is what they're optimized for. That's where you have, all your data able to fit within a universal schema, star schema, and where you have limited types of queries that you do. Amazon Redshift would be an excellent option for that. If you want to expose Presto to large numbers of users via the web, there's a UI service called AirPal. It was developed by Airbnb. It gives access controls for users, so you can have user accounts with passwords. You can use it to browse what the available tables are. You can look at the metadata, the partitions, the schemas. You can even look at sample data. You can write queries in a query editor that's easy to use. You can submit the queries through the web interface. You can track the progress of those queries. You can take those results that you get back and output them, or you can look through them on the browser, but you can also take them and create a new Hive table based on the results of the query. And you can save the queries once you've created them and go back later to review them or re-execute them. All right, so let's continue with our demo. I'm going to do screen sharing here. All right, so let's see. I'll just refresh the screen, make sure we've got the Okay, so we're still waiting for the task nodes to come up. All right. I have a cluster that's already running that I can probably use. I'll come back to this to show you that these nodes do in fact become available. We're just waiting for the task nodes. All right, let me switch to a cluster that's already up and running. All right, we'll do this one here, demo. Okay, so this one's already up and running. We've got exactly the same configuration that we asked for. We have 10 task nodes. The hardware is shown here, so we've got all that. By the way, the dynamic resizing up or down of the cluster, that's available just from a click there. All right, so what we're going to do, this cluster is already running. We're going to SSH into the cluster. You do that by clicking on the SSH link, and we grab the convenient command line summary that it's provided for us. And then I'm going to switch to the terminal and paste that in here. All right, so we're SSH'd into the cluster. We're in the master node. Get a splash screen confirming that. And now what we're going to do is run Hive. All right, let me see. Okay, so we don't have any tables. We have a nice clean slate here. So what I'm going to do now is create or expose that data set that was on S3, the air flight data that we had. I'm going to expose that as a Hive table. Now to do that, I have this, what we're doing is essentially as an exercise, and we'll share a link to this later, but I'm going to take the, let's go down to the Parquet version. I'm going to take the create external table command here, and we're going to copy that. Scrolling down. Oop, there we go. All right. So we're going to take this and copy it. Take notice of, we've got a pretty wide table here. It's 115 columns. It's partitioned by year. Okay, as I showed you, the year equals 1987 was the example we showed. In this case, instead of CSV, I've transformed the data into Parquet. The reason I've done that is Parquet is an excellent storage format that is a columnar storage format. What that means is when you perform queries where you're selecting on a certain number of fields, the only parts of the data that actually get touched are the columns that you specify in the SQL. That's in contrast to a row-oriented storage format like CSV. CSV, when you perform the queries against it, the entire row has to be handled during query execution. So if you have a wide table as we do, 115 columns, that would add more delay than we might like to have. With Parquet, we're only handling the columns that we ask for. And then the key thing here is we've indicated that the data lives at that same bucket, but in this case, we've added the Parquet path to it. Okay. All right, so let me switch back to our, the terminal. There we go. All right, so I'm going to paste that into Hive. Okay, so Hive now has this interpretation available to it. What we want to do, because of the partitioning, we're going to tell the Metastore, we're going to do the Metastore check, repair table air delays par, I called it. All that does is synchronize the EMRFS component that I talked about, synchronize that with the data on S3 and the layout in terms of partitions. So here you can see it's adding those partitions. All right, so that's it. We've got our table defined. We can exit Hive. Hive is still running in the background. That table still is defined, and it's available to any service that wants to query that data set sitting in S3. Now we're going to run the Presto command line. Okay, and we're going to issue some SQL queries. So let me go back to my exercise here. We're going to query. So let's take a couple of examples. As I said, this is an air flight data set that includes things like delays, includes airlines, departure points, destinations, how long the delay was, et cetera, the time, and so on. So we're going to try to answer the question, over the 29 years of air flight data, which months have had the greatest number of flight delays? Okay. And we do that by taking this SQL statement. Okay, we're going to copy and paste that in. This is doing a group by, so it's going to look across the 29 years and do a roll up and summary of that data. So let's go back to our here. Okay, and so I'm going to paste that in. Oh, what did I do? What did I do? Select months count. Oh, I know. I need to tell Presto use Hive default. There's a namespace that our table was defined in. So now I can execute that. And you see a few statistics. Boom, 29 years of data. We've done the group by, rolled up the results, and you can see there's 29. And you can see the month breakdown. So it looks like December, probably Christmas, and summer months, I guess, July. So that's that example. All right, let's do another query. So I'll switch back here. Let's answer the question, which airline carriers have the most numerous departure delays? This might be something you want to check before you book your flight. We'll take this query. Again, it's also a group by, but now we're rolling up based on the unique carrier delays instead. Let's go to, okay, paste that in. All right, and so we have the unique airline code, carrier codes here, and we've got the number of delays in sorted, descending sorted order. All right. So there's a bunch of other queries you could run. In this exercise, there's a link to where the source data was or is, and it's from the Bureau of Transportation Statistics, and they've got a definition of the table. So if you want to understand the semantics of the fields and the type of data that's present, it's got a full description there. If you wanted to download the raw data, you could do that. We will make this data available for public consumption. You can get it from my S3 bucket. I've opened it up for people to access, but we'll put this into the AWS public datasets collection. All right, let's go back to the slides. So I'll go back to, all right, so let's summarize things. So to query the data with Presto, running on EMR, with all the data sitting in S3, with all the benefits that S3 has, with all the benefits of this decoupling of storage from compute. We have data in S3 is queryable using Presto on EMR. You've seen that now. Presto is easy to deploy on EMR. You saw that. And we'll switch to the cluster we spun up shortly just to show you. Presto provides ad hoc queries, supports a wide range of data sources. It's fast, it does pipelining, it's feature rich, it's an ANSI SQL query engine. There's an increasing adoption, including production deployments and an active developer and support community. Okay, let's just briefly go back to the web console. Let's see, and actually, where's the just speed, I guess. Okay, so you can see we've got our nodes running now, and so we've got everything up and running. It was running for because we were going through slides. All right, we'll go back to the slides. Okay, so that's it.
Great. Okay, thank you so much, Keith. We are about out of time here, so we're going to go ahead and wrap things up. Special thank you again to Keith for his time and a great presentation, and to the moderators, Jorge, Kevin, and Chris, for answering your audience's questions. If you have any comments on our previous or upcoming webinars or suggestions on topics you wish AWS will cover in future webinars, please feel free to send us an email at aws-webcasts@amazon.com. Your feedback will help us to improve our webinar programming. Thanks again to the audience for taking the time to join us today, and enjoy the rest of your day.